Let me talk just a little bit about electric field lines. So basically the idea of the electric field, right, is that it's the direction that a positive charge would start to move, or the direction of the force, technically, right, on a positive charge. So if we put a positive charge between these plates, the left side here is positively charged, right? And that would cause, we got to have blue pen, right? That would cause the rightward force on this positive charge, right? So the electric field between these plates will be to the right. It'll be from the positive to the negative. Now, remember that if we place a negative charge there, it's going to experience a force in the opposite direction. But this is all well and good, because remember the force is just EQ, right? And if it's a negative charge, that number becomes negative, and the force is just opposite the direction of the electric field. So this all works. Okay, things get interesting, though, when you start to get conductors. We'll talk about that in a little bit here. So this picture here, this is an electric dipole. So we've got a positive charge here, a negative charge there. Notice that these field lines are in general away from positive toward negative charges, right? If we put two positive charges, these lines will actually bend away from each other. And two negatives would do the same thing. You get the same pattern as this. Okay, now let's look at some conductors. Conductors are interesting, right? Because conductors are going to induce charges. So for example, if this conductor is, we put a sphere around a little isolated positive charge, the inside of the sphere will charge negatively and the outside will charge positively. So if you look at one of these field lines, it'll go from here to this negative charge, and then it goes away. Why does it go away? Well, because in this region right here, there's this field from this guy here that's this way, right? But then there's also the field due to the induced charge, right? That's this way. And those two fields are going to exactly balance each other out, because if they don't, then there is an electric field, and the electric field will cause the charge to move. The only time that the charge stops moving is when that electric field has gone away. So inside conductors, the electric field is zero. Okay, that's kind of cool. So if we let me show you another example of this. Let's imagine that we've got this external thing, these plates here that are, this is, say positive 12 volts, right? This is 0 volts. And we've got this, nice electric field. It's distorted slightly at the edges, as you'll discover in the lab, okay? But then we stick this little box in there, this little cage, a Faraday cage in there, right? Notice that the external field, that this piece of metal in there gets negative charges toward this positive and positive toward that negative. Okay, how much does that build up? Well, it builds up until there's exactly no electric field whatsoever in that space. And the reason that there's none is that there is an electric field to the right due to the external, but there's an electric field to the left due to the induced charge. And those exactly cancel each other out, because if they don't exactly cancel each other out, the charge will move until they do. Right? If the electric field is not zero, then charge moves in such a way as for there to be zero. Right? Let's imagine we stick this in here at first. Right? At first, this is going to be all equally, the charge will be distributed equally, positive and negative, right? But then pretty soon we start to get negatives on this side, positives on that side, right? Let's imagine that there's not enough, though, right? So we've got this external field that's like this. Right? We've got an internal field that's not quite as big because not enough charge is moved, right? Well, if there still is this residual bit of this external field, then more electrons are going to run over here. When are they going to stop? They're going to stop when the external field is exactly the same size as the field generated by the induced charge on this little guy here, this thing that's in the middle. So charge will move in order for there to make zero electric field inside the conductor. This is good news. So if you're in a lightning storm and you're in your car and you're unlucky enough for lightning to strike the tree or strike the car, okay, that's bad because the electric field could, tear you apart and kill you, right? But you're inside this car, and as long as you're far from those windows, okay, the charge is going to stay on the outside of the car, and the electric field is not going to change inside the car. The car protects you from that. So to some extent, a car can be like a Faraday cage or something like that that prevents the electric field from changing inside of it. Okay. The other thing that's kind of cool is that if you've got a conductor like this, if there is an electric field that has some component parallel to the conductor, then charge will move along that conductor until all the electric fields are perpendicular to this conductor. So by default, electric fields will always be perpendicular to a conductor. If it's not perpendicular, then charge moves along the conductor until it is perpendicular. And this is something we'll see in the electric field mapping lab. It's hard to see with the PhET simulation, so that's too bad. Anyway, I don't know, maybe I can visualize it some other way. I'm trying to picture that. All right, good enough.